In mathematics, a Lissajous curve, also known as Lissajous figure or Bowditch curve, is the graph of a system of parametric equations which describe complex harmonic motion. This family of curves was investigated by Nathaniel Bowditch in 1815, and later in more detail by Jules Antoine Lissajous in 1857. The appearance of the figure is highly sensitive to the ratio AB. For a ratio of 1, the figure is an ellipse, with special cases including circles and lines. Another simple Lissajous figure is the parabola. Other ratios produce more complicated curves, which are closed only if AB is rational. The visual form of these curves is often suggestive of a three-dimensional knot, and indeed many kinds of knots, including those known as Lissajous knots, project to the plane as Lissajous figures. Visually, the ratio AB determines the number of lobes of the figure. For example, a ratio of 3/1 or 1/3 produces a figure with 3 major lobes. Similarly, a ratio of 5/4 produces a figure with 5 horizontal lobes and 4 vertical lobes. Rational ratios produce closed or still figures, while irrational ratios produce figures that appear to rotate. The ratio AB determines the relative width-to-height ratio of the curve. For example, a ratio of 2/1 produces a figure that is twice as wide as it is high. Finally, the value of I determines the apparent rotation angle of the figure, viewed as if it were actually a three-dimensional curve. For example, I equals 0 produces x and y components that are exactly in phase, so the resulting figure appears as an apparent three-dimensional figure viewed from straight on. In contrast, any non-zero I produces a figure that appears to be rotated either as a left-right or an up-down rotation. Lissajous figures where or equals a1, bar equals n and are Chebyshev polynomials of the first kind of degree n. This property is exploited to produce a set of points, called Padua points, at which a function may be sampled in order to compute either a bivariate interpolation or quadrature of the function over the domain, -1, 1, -1, 1. Examples: the animation below shows the curve adaptation with continuously increasing fraction from 0 to 1 in steps of 0.01. Below are examples of Lissajous figures with I equals I/2, an odd natural number A, an even natural number B, and or AABA equals A1. Generation: prior to modern electronic equipment, Lissajous curves could be generated mechanically by means of a harmonograph. Practical application: Lissajous curves can also be generated using an oscilloscope. An octopus circuit can be used to demonstrate the waveform images on an oscilloscope. Two phase-shifted sinusoid inputs are applied to the oscilloscope in XY mode and the phase relationship between the signals is presented as a Lissajous figure. In the professional audio world, this method is used for real-time analysis of the phase relationship between the left and right channels of a stereo audio signal. On larger, more sophisticated audio mixing consoles, an oscilloscope may be built in for this purpose. On an oscilloscope, we suppose X is CH1 and Y is CH2, A is amplitude of CH1 and B is amplitude of CH2, A is frequency of CH1 and B is frequency of CH2, so AB is a ratio of frequency of two channels. Finally, I is the phase shift of CH1. A purely mechanical application of a Lissajous curve with A equals 1, B equals 2 is in the driving mechanism of the Mars light type of oscillating beam lamps popular with railroads in the mid-1900s. The beam in some versions traces out a lopsided figure-8 pattern with the 8 lying on its side. Application for the case of A equals B. When the input to an LTI system is sinusoidal, the output is sinusoidal with the same frequency, but it may have a different amplitude and some phase shift. Using an oscilloscope that can plot one signal against another to plot the output of an LTI system against the input to the LTI system produces an ellipse that is a Lissajous figure for the special case of O equals AB. The aspect ratio of the resulting ellipse is a function of the phase shift between the input and output, with an aspect ratio of 1 corresponding to a phase shift of and an aspect ratio of corresponding to a phase shift of 0 or 180 degrees. The figure below summarizes how the Lissajous figure changes over different phase shifts. The phase shifts are all negative so that delay semantics can be used with a causal LTI system. The arrows show the direction of rotation of the Lissajous figure. Logos and other uses. Lissajous figures were commonly displayed on oscilloscopes meant to simulate high-tech equipment in science fiction TV shows and movies in the 1960s and 1970s. Lissajous figures are sometimes used in graphic design as logos. Examples include, the title sequence by John Whitney for Alfred Hitchcock film Vertigo is based on Lissajous figures. The Australian Broadcasting Corporation, the Lincoln Laboratory at MIT, the University of Electrocommunications, Japan. In computing, Lissajous figures are in some screensavers. A Lissajous curve is used in experimental tests to determine if a device may be properly categorized as a memristor. See also, Rose curve, Lissajous orbit, Blackburn pendulum, lemniscate of Gerono, notes. External links, Lissajous curve at MathWorld, interactive demos, 3D Java applets depicting the construction of Lissajous curves in an oscilloscope, tutorial from the NHMFL, physics applet by Tuking NG. Interactive Lissajous curves in Java are Eurographical representations of musical intervals, beats, interference, and vibrating strings. Simple HTML5 Lissajous curve generator a Euro allows controls for A and B as integers from 1 to 12 each. Interactive Lissajous curve generator a Euro JavaScript applet using JSXGRAPH, animated Lissajous figures.